Okay, so today we're going to talk about dynamic behavior of ideal systems, and this content is going to come from Chapter 6 of the Chemical and Bioprocess Control. So for this chapter, really what we're going to do is we're going to look at using essentially the form of the transfer function to be able to predict how a process will respond. And we can do that, or how it will respond to a certain type of input. And essentially what we're going to be able to do is we're going to be able to predict or sketch the time-dependent response by having the transfer function as written in the Laplace domain. And then there's useful things that this can be doing. The benefit, or the most important thing, or the most practical benefit of this topic is going to be for controller tuning, which we'll start looking at in the next couple chapters. So it's useful to understand the dynamics of a process, and by looking at things like characteristics of the behavior, which can be response time, gain, and then sometimes things like, how much oscillation there is in a process, we can determine what the tuning parameters should be for the process. So a couple things I want to just give you a quick idea about. So we're going to focus on two things. One thing that we're going to look at is we're going to use the Laplace domain transfer function. So knowing the Laplace domain transfer function, we're going to be able to sketch the dynamic behavior to a step change in the input. Okay, so we're always going to be looking at the response to a step change in the input. Now, just to kind of give you a little bit of an overview, we're primarily going to look at maybe only 4 or 5 different types of functions. So we'll have 4 or 5 transfer functions, and based on those 4 or 5 transfer functions, we can sketch the dynamic response. And by saying 4 or 5, it's really more like 2 with slight differences to them. Okay, so that said, we're also going to be able to go in the opposite direction. We're going to look at, given a process response, so if we know what the dynamic behavior is in the time domain, so for example, if we're actually working on a real process and we apply a step change into the input, we'll watch the response. We're going to be able to look at that response and then predict or derive or calculate or come up with a transfer function for that process. Right, so we can take process data and sort of come up with a transfer function that describes how that process behaves. And again, the same sort of thing is, my expectation is that you can do that for really these 4 or 5 different types of processes. So that's the overall, those are the 2 primary objectives for this chapter. Take a transfer function, sketch, predict what the time-dependent response is for the control variable, for the final output, or look at the process, look at the actual data, and then come up with a transfer function that would represent that data. And again, the input, we are always going to focus on an input which is a step change. And the step change could be something to the specified flow rate or set point, something like that. All right, so as I said, we're going to focus in this, we're going to focus on the dynamic response of the output of the overall process response to this type of function. So this is what a step function would look like if we plotted right here. So this, for example, could be our main input. So this, for example, could be f specified as a function of time. So at some time, and we can designate this t equals 0, we applied a step change in the input. And if we want to just throw some numbers on here, maybe this could be something like it started at 2.0 GPM, and maybe we made a step change to 4.0 GPM. All right, so that's an example, but this could be an example of a step. And so, and again, remember, because transfer functions are in terms of deviation variables, we were kind of looking at the response, or the input in terms of deviation variables. There are other types of inputs that can affect the process, and this inputs can be in terms of the specified or disturbances that affect the system. There are things that can look like this pulse right here. So instead of having a step change, what we can do is that we can have a process, and we can apply like an impulse. So we can increase the specified flow rate for a certain amount of time, have it come back and settle down. Some of the benefits of doing this is you can look at and seeing how certain types of things propagate through the system. So you can imagine this is if you had a mixing process and for a second you put like a drop of food coloring or something, you'd sort of see how that how that color sort of diluted its way through the process. And so we can do this in various types of parameters. Again, representing, so there is a little bit of a discussion in the textbook, and I mean, these are things also, you can find these online as well. We can represent this type of step change using a mathematical relationship. So just like in this case right here, we know that the equation or the model for this process would be something like, F equals F specified at T equals 0, so, or F specified plus A, or the model for this would be something like F specified equals, F specified 0 plus A, right? And this would apply at T equals 0. So something like this is a little bit harder to represent in terms of what the change would look like, is because at some sort of time, at some time period, we have this addition, and then after some time period, we have a decrease. And so I'm not gonna tell you what the exact relationship, but you can think about what this would be. The way you can create a function that looks like this is essentially you have a sum of two functions where one of them has a dead time, or one of them has a lag associated with this, right? So this function could look like what we have here, plus another function that has a lag. And think about what that might be in order to get this to come back down to 0. And again, this is not something that you're gonna have to necessarily do or be responsible for, but I think this is a very creative thinking type exercise. We can also represent a function that looks like this. So this would be a ramp input. So what this would mean is that, we slowly increase an input to the process, like maybe electric heating or something like that. And then there can also be a sinusoidal input shown here. So where you add, like maybe you have an oscillation, and this could be in terms of the flow. We'll look at this later when we look at frequency response. So by doing things like varying how fast the oscillations are and how much the oscillations, we can actually look at essentially how these oscillations propagate through a process, and we can use that to determine where it's important to apply control to. All right, so various things of doing this. Again, what I want to remind you is that we're gonna, again, for this topic, we're gonna focus on, this is what our input is, okay? And so we are going to be looking at y of t. So we're gonna be sketching y of t. Now remember, ys equals g of s times u s, right? So based on the form of this right here, we can calculate this. Now the point of this chapter is to avoid doing all of the math, to derive the transfer function, multiply it by the input. And again, in this case right here, we said the input is a step function, which is going to be a over s. But again, we don't have to multiply g of s by this in order to do this. We're just looking at the form of the transfer function. This is saving us from doing all the math to convert it to the time domain and then sketching the function in the time domain. Okay, so again, the important things are, we have the output variable response, looking at that in the time domain, so the dynamic behavior of the output variable, based on knowing the transfer function of the process. And the transfer function of the process is what relates output to the input in the Laplace domain. And we're going to be doing this for step functions, which are a over s in terms of the input. Okay, so the first process that we're going to start with is a first order process. So first order process is essentially the simplest, or one of the simplest forms of what a process would be. So again, then these are things that maybe, or at some point might become second nature to write these down. So the differential equation for a first order process, as we said, it's tau times dy, and so y is our variable, it's a function of time, dt. So tau plus the derivative of the function plus the function equals kp times the input function, which is u of t. So this is a first order process where we have the time constant, which tells us how fast the change is. And then we have Kp, which tells us the gain. So if we go through our process of deriving the transfer function from a first order differential equation in terms of deviation variables, remember when we go from here to here, we are using deviation variables. The transfer function for a first order process is always going to look the same. So again, G of P equals, it's going to be the output over the input in the Laplace domain equals Kp over tau P S plus 1. And again, I'm going to note, so one of the things that's going to be that's going to be important here is we're going to need to put this into standard form. So for the analysis that we're going to do in this chapter, or for the analysis that we're going to do here in terms of using transfer function to sketch the dynamic behavior of the output variable, or take the data and convert it to a transfer function, we have to have it in standard form. And to have it in standard form means whatever this kind of term on the bottom is going to be plus 1. So we have a polynomial, and then the constant of the polynomial has a plus 1. And we'll look at a couple examples to see how that works. Maybe I'll do a little bit of a tangent right here just because it's important. If I have something that's like, if I have a transfer function that looks like 2 over 3s plus 2, s plus 1 plus 1, this right here is not in standard form, because if we multiply out the polynomial and we look at what the constant is in the denominator, it doesn't have a plus 1 as a constant in the denominator. It would actually be, this would give us a plus 2 plus 1, which would be plus 3. Even if this was 1, we would have a 1 plus 1, which would be 2, and it's still, this would not be standard form. Okay, so this is, so given a first order process, we are going to look at sketching the dynamic response. I'm gonna stop trying to maybe beat a dead horse and reminding you of this, but I'm going to do it one more time. Remember, if we want to go, we are just looking at this transfer function. We are looking at the transfer function, which is this right here, right? So again, if I want to calculate, if I want to get y of s from here, this is going to be Kp, which is a constant, over tau P s plus 1, which is a constant, times u of s, which is the input. And again, we said we're looking at the response to a step input. A step input would be a over s, right? So now we're looking at, now this would be the overall function. So if we want to now go to get yt, we have to do inverse Laplace. And we could do that for this one because this actually form shows up in the table because it's a common form. But to do anything maybe more than this would require a little bit of math. But again, what I want to remind is that all we need is this right here to get this right here. And so sometimes people like to add this term to here, and it can make it a little bit confusing. So I'm trying to just get that point, drive that point. Dynamic response based on transfer function. So for a first order process, this is what a first order process will look like. This is how the response will look. Okay, so what this plot shows is plotted on this side over here, we have y. I guess these would sort of have to be on different axes. So we have y over here, and we have u over here. So this term right here, our delta u, is what we would call a, so the magnitude of the step change. And then if we look at our y, and then I guess over here on the bottom axis, it says time. Just write that again. Okay, so a first order process will look like this. So at t equals 0 is where the change was made. So initially, our process was at a steady state value for a steady input. As soon as we applied that step input change, the first order process will always look like this. It'll initially start changing very steep, and then it'll slowly approach the new steady state process, right? So we can determine what this new value, what this new steady state value is based on information that's given in the transfer function. Okay, so there's a couple different ways we can refer to characteristics on the plot, and so I'm going to kind of point out a couple of things. So we can call this term right here, we can call delta y. So the delta y, we call delta y as in what is the total change in y from the initial steady state to the new steady state, and then delta u is essentially our step in our essentially a, which is the step change in the input. So one thing that we know is we already talked about what gain is. So gain, Kp, equals delta y over delta u, or again, we could say delta y over a because delta u is equal to a. Okay, so that's one thing. And so this right here is given. This right here is given from the transfer function. So if we're given a first order transfer function, we know what the overall new value is going to be in response to the step change to the input that was made. Right, so now in terms of plotting this, we can now plot the initial value, and then we can plot some value over here as time approaches infinity. There's two other points that we can plot on here, or there's actually multiple, but there's two other that we define. And I would say generally, if you can plot these 2 points, you can essentially just hand sketch what the response is through there, right? Because it's going to follow this type of behavior. So these 2 points are going to be at tau and at 3 tau. So this term tau p comes from the transfer function, so that was given. And this term 3 tau p is just 3 times that value. So for a first order process, based on the gain, based on the tau, the value of y, the value of your function at 1 tau is going to be about 63% of the total change. So 63% of the total change is essentially your gain times a. So this term right here, a times Kp is essentially delta y, right? This delta y right here is equal to the gain times delta u, which is a. So 63% of that total gain is going to show up at 1 tau, and then at 3 tau, we're going to be 95% of that. Okay, so the way that we would go, knowing the transfer function, we can first come up with this point, or this is based on the initial steady state value. If we plot this in deviation variable, this would be 0. We can plot this point right here, and then based on using tau, we can calculate 63% of the total change, 95% of the total change, put these 2 points on here, and you just sketch it through. So that would give us a pretty good representation of what the response is to the process. Now, every first order process is going to respond this way, but most processes are not ideal first order processes. Okay, so that's the response for a first order process to a step change. So here's some information. This is this sort of information that's given that we talked about a little bit. I'm going to say something right here. The book talks about this thing in terms of settling time. So this is about when it gets to the new steady state value. It's about 100%, like 99 point close to 100. I don't like this at all because once you start having noise in there, it's kind of hard to distinguish the noise from where you are. So for a first order process, use this behavior, use this plot. Don't use settling time. This isn't necessarily very useful. Where this is useful is sometimes you can estimate you can sometimes estimate tau of a process if you know the settling time. So if you're given experimental data from the settling time, you can get the gain from how much it changes, and you can estimate tau p. It's actually better to estimate tau p from 63% because if you have data that has noise that looks like this, right, it's kind of hard to tell when you actually get to the new steady state value. But if you sort of draw a line through the new steady state value and a line through the current value, you can pretty much get what 63% is of that value and figure out where your tau is. So that's a little bit better metric to calculate tau. Okay, so as an exercise, let's go ahead and do an example. So let's sketch the response to a process that has this as a transfer function. Okay, so the first thing we have to do is put it in standard form. This right here is not in standard form. So this right here, in order to get it in standard form, we divide everything through by 8. So this would be 0.5s plus 1. Now we know gain, and now we know tau p. So based on the gain and based on tau p, we can go ahead and sketch the response for this sort of process, for a process that has this as the transfer function. So I'm just going to put this on start t equals 0 right there, and just kind of give a few increments in terms of tau p, 1, just for these. So these are, this right here would be, in terms of time axis, this would be tau, or no, I'm just writing, this is in terms of maybe minutes or in terms of time. So that we have 1, 2, and this, we'll call this time in minutes. And again, the transfer function would have to have units associated with it. So this right here is typically going to be something like how much change over something, and then the units on the S will be in terms of time. So it could be minutes or seconds or hours, depending on the process. Okay, so we can plot, also, I might do U on this side, and I'm going to plot Y on this side. So for U, we'll have a change of, just to keep it simple for now, we'll say U changes by 1, right? On the U side, this is 1.0. And then on the Y side, we'll start our Y right here. And so because the gain is 8, we know the process should change by 8. 1, 2, 3, 4, 5, 6, 7, 8. So the process is initially going to be at an initial condition, and then at some much later time period, it's going to be fully responded. Right, and then we know that at 1 tau, it should be 63% of that change. So 63% of 8 shows up for 1 tau. 1 tau is 0.5, so at 1 tau right here, I got to be 63% of that. And again, this value is 0.63 times 8. And then we can also count at 1.5. This is going to be 3 tau. So at 3 tau, we'll have another point. And this other point is going to be 0.95 times 8. And then we can just kind of sketch our process response. It's going to look something like that. Okay, so this would tell us what the response of, so we can know if we have a first order process, it's going to look something like this. All right, so not necessarily a lot to that, we can do that. First order. Okay, so now we're going to in addition to a first order process, we're going to look at second order processes. So a second order process, we can write the differential equation. Again, it's, let's see, so for a second order process, I'm going to write tau p squared dyt dt squared, so second derivative of y plus 2 times zeta times tau p times dy dt dt plus y of t, the function, equals kp times u of t. So you see some similar parameters in this one. We have kp, and kp is still the gain. Tau p is still the time constant. So now, in terms of, if we write a second order function, we can always, or if we have a second order differential equation, we can always divide through the constants such that there's a 1 in front of y of t, and that's standard form. So maybe now you can see a little bit about where that 1 in the denominator comes from. It comes from having this as with unity as its constant. When this has unity as its constant, the constant in front of u is the gain. The constant in front of the second derivative is tau squared. And then instead of calling this a different constant, we define it this way because we can get information about the process based on the value of this term. And it really matters whether or not this term, how much this term is from, is between 0 and, some positive value or negative. Okay, same thing, we can go and we can derive the transfer function for the transfer function for the second order process is going to look like Kp over tau p squared s squared plus 2 zeta tau p plus 1. Just to point something out as well, the book will interchangeably use tau p or tau n. It doesn't matter what we call tau as long as we have a unique tau for each different process. I try to be, if I'm talking about the actual chemical process, not the actuator, not the sensor, or not the controller, I try to call it tau p. You can call it tau n if you want. It's just n order process. So for a second order process, we could call it tau 2. It doesn't matter as long as we have a unique identifier for tau for the specific process. Okay, so the definition. So here we still have gain and we still have time constant. Those are the same thing. And now we have what's called a damping factor. So this term zeta is a damping factor, and the damping factor is going to tell us essentially how fast the process dampings out. So a second order process can look a couple of ways. If we plot y versus t for a second order process, if the process is what's called underdamped, that means it'll have oscillations. So a second order process can look something like this. Or a second order process could look like this. And really it all depends on what the value of this term is. I mean, I should say also, the second order process can also look like this. We can have, wait, that's not drawn very well. Second order process can also look like this with kind of growing oscillations. And so that would essentially be second order unstable, where it's essentially growing. When we look at stable second order processes, they can have oscillations or they can not have oscillations. If it doesn't have oscillations, it's what's called overdamped, which means the process is essentially already dampened out. What damping means is how fast these oscillations go away. So if you're thinking about, maybe intuitively about what the term damp means to kind of, compress something, it's how fast these compress. So what I'll kind of tell you, and we'll see this a little bit more, is that if this value right here, zeta, if zeta is greater than or equal to 1, the process is going to look like this. So zeta equals 1 is what's called a critically damped process. If zeta is greater than 1, the process itself is going to sort of look like a first order process. And how I should have done this actually is there's actually it's not a sharp turn on, but it's more of a delayed turn on. If zeta is less than 1, but now I'll also say greater than 0, because once zeta gets less than 0, we put a negative right here. And if you remember, if we have a negative right here, looking at the denominator of this transfer function, a negative right here would indicate that this process would be unstable, and it would look more like something like this. Okay, so if zeta, damping factor, is between 0 and 1, it's going to have oscillations that look like this. The closer the zeta is to 0, the more it's going to look like this type of sustained oscillations. The closer zeta is to 1, it's going to look more like this damp type process. Okay, so that's why this is written this way, so that we can calculate the damping factor, and based on knowledge of the damping factor can tell us about how much oscillation there is in the process. If you want to speak about processes in terms of, generally, if you can calculate the damping factor and you show it's like 0.5, you can just say, well, the process has oscillations, I know that, and they'll, not severe, but it has oscillations. Okay, so this shows some plots a little bit about what we're talking about. And so critically damped process, so here we're looking at the response. So critically damped process is this right here. And essentially what this means, this is right on the border of having oscillations. If that value were just a little bit smaller, so that second value in the denominator in front of the S term was just a little bit smaller, this would have oscillations. Overdamped is going to look like this. Underdamped is going to look like this. So we look at this, you might say, well, critically damped looks like it's the best because it doesn't overshoot. But the difference though is overdamped is a slower response. Underdamped is a faster response. So sometimes it's favorable to have a process that has a conservative or slower response in order to maintain better control for another process. So for example, if you have storage tanks that are used to store reagents, you might have the level of those tanks be extremely overdamped because you don't really care about what the level is. You just want to maintain some other aspect of the process. Underdamped process is something that responds fast. It does have overshoot, but you can see it has overshoot, but it gets to this new steady state value a lot faster than the critically damped process, and sometimes that's beneficial. Okay, so this slide shows the effect of zeta on an underdamped response, and this is sort of what we talked about a little bit before. So again, I'm just going to highlight here. Here's the critically damped process. If we want to go a little bit more, we can. If we want to overdamp would just make it a little bit more sluggish. As we approach zero, you can start to see that the speed of the response. So right here is our new steady state value. As zeta gets smaller, we get to that new steady state value a lot faster. But the trade-off is we have more oscillations. Ideally, we'll see that when we design a process and add a controller and tune the process, we're going to tune the process based on these criteria. And the reason why, so we can change the values of the controller to affect how much this oscillation occurs. For what we're doing now, when we look at a second order process, the amount of oscillations and the amount of damping that it has is just what the process has. We can't necessarily change that or not, but we can just see what it is. When we add a controller to the process, we can change the values on the controller, which are going to affect this damping rate, this damping factor. So that's the importance here, is we can change controller settings to affect what the damping factor is. So again, if we want to have a process that responds really fast and has a lot of oscillations, we can. Again, I can go probably do one more. I can say if zeta equals 0, again, if we know zeta equals 0, it's going to look something, essentially it's going to be sustained oscillation. So there's going to be no damping on the process. Okay, overdamped process, kind of like what we talked about there before. As we increase the damping factor, we just make the process respond a little bit slower. Okay, on this slide, we're going to talk about the characteristics of an underdamped. So I guess I'll tell you, if we have an overdamped second order process, we're going to treat that differently. So the only type of process that we care to treat, or that we look at, the only type of process, the second order process that we care about in terms of this analysis, is an underdamped second order process. So this plot right here shows essentially what the characteristics of the response. So these are the characteristics of the dynamic response. Okay, so the first term, this has something called rise time. I'm going to call this something else. I'm going to call this R. Rise time, this is a characteristic. So for ideal, if you have an ideal second order, this characteristic right here, R, which I call R, the time that it takes for the process to reach the new steady state value. For an ideal second order process, R equals T rise. But if we just want to call it a plot characteristic, T rise is a characteristic of a model. I like to call R a characteristic of the response. And those two things are slightly different, and this might make more sense in a little bit. Okay, so the term D, so this is essentially, we call this D, this is essentially what we called before delta Y, so the overall change in the process. So so we can get that based on what is the steady state value. B, this value right here is what is the overshoot. So how much does the process go over the new steady state value? C, this is the second overshoot peak. And then again, we don't really define it past the second peak. So if we know how much the process decays for the first peak, and if it's an ideal model, it's going to essentially decay by the same amount as it continues to go forward. Other characteristics that we have is T. T is the period of oscillation. So again, we're looking at one full oscillation. We can define multiple T's on here. So we have essentially this right here would also give us T between the first oscillation. We can look at the second set of oscillations. We can look at this. So a lot of times to define T, I try to take maybe at least 2 periods of oscillation and kind of average them out a little bit. So this is the response for the characteristics of a second order response. There's also something called decay ratio, which is just shown here. For the second order processes, we can relate these characteristics to each other, and then there is a set of equations. So based on knowing these parameters, right? So if we have a process response, we can determine these parameters, and from these parameters, we can get Kp, we can get tau p, and we can get zeta for this process. Okay, so an example of a second order process would just be something like shown here. So for example, this is a closed loop performance of a first order process with a PIO controller would look like a second order process. If we make the process, like I said, if we make it very aggressive, so respond fast, or if the aggressiveness is low, so it's a conservative process, it'll be overdamped. But if we make it very aggressive or respond fast, it's going to become underdamped. So I want to use this example right here to kind of to go through and take a transfer function and sketch the process response. And so we can go ahead and we can do this going back and forth. So again, this has to be in standard form. So to put this in standard form, I'm going to go ahead and multiply everything through by 2. So 2 over 4s squared plus 3s plus 1. Now based on this, I can determine what the parameters are. So Kp equals 2, tau p equals 2. So this is tau squared. And then I know that 2 tau p, so I know this term right here is 2 tau p zeta. So this is 4 times zeta equals 3. So therefore, zeta equals 3/4 or 0.75. So now, knowing these, so again, given a transfer function, the first thing that I do is put it in standard form and get these parameters, part 1. Part 2 is I want to calculate, using these parameters, I can calculate D, which is the, essentially like previously, it's the gain times, it's the, what the gain times delta U, the change in the input. I can calculate B, which is the overshoot. I can calculate C if I need. I can calculate T. And then I can also calculate T rise. Okay, and these are going to be based on equations that show up in the textbook. I will introduce a couple right here. So I'm not going to necessarily calculate all of them. But for example, so we know B over D equals, this is what's called overshoot. So overshoot is B over D, the ratio of the overshoot to the total change is equal to the exponent of negative pi times zeta divided by square root of 1 minus zeta squared. Okay, so if we're looking at sketching the process response, which is our third step once we have these, I'll say first thing that we can know is that at some point our process is at an initial condition, and this right here is t equals 0. And again, here we'll just say delta U equals 1, just to make it input is 1. So we can get, based on knowing what the gain is, so here the gain is equal to 2. So we know at t equals infinity, the process should be at 2. or again, and this is in terms of deviation variable. So the deviation variable, the initial value is 0. At the new steady state, it's going to be equal to 2. Okay, so we can kind of sketch that point on there knowing gain. So essentially, we've used our gain. The next thing that we can do is we can use the value of zeta. So I guess also, if we know this, we also know this is going to be our D parameter, D equals 2. Now we can use the zeta to calculate B. So we can calculate B equals whatever is for this process. And again, it's going to be overshoot is going to be, we can kind of sketch a line up here. So B should be somewhere up here. Okay, we can get that. The next thing we can do is we can calculate the period of oscillation. So the period of oscillation T equals 2 times pi times zeta over, or T equals, that's not correct. Okay, 2 pi times tau P divided by square root 1 minus zeta squared. And so then again, B is going to tell, this is going to tell us the period of oscillation. But the thing though that we need first is we also need to calculate rise time. So the rise time, all right, so again, we just go through this process and let me see. Actually, I need to pull my textbook to get rise time. But I just want to give you this equation in case you don't have the notes in front of you. So for the second order process, okay, T rise is going to be equal to, let's write this on here, tau P times theta minus phi divided by 1 minus the square root of 1 minus zeta squared. And so then we also need to know this term right here, phi. And I'm running out of space a little bit, but phi equals, actually, I'm going to write this somewhere else. For now, and I know this is not ideal, I'm going to write it right here. So phi equals inverse tangent. And I just wanted to write it here so I can write the equation properly. 1 minus zeta squared over zeta. Okay, so this is the value of phi. So phi would go in here, and so this would give us rise time. So the rise time tells us the time that it takes from when we made the step change to when it crosses the new steady state value. Okay, so that would be T. Now, knowing the period of oscillation T, that means knowing the, so here's rise time would be here. Knowing the period of oscillation, we can kind of put a point on here. We can put another point on here. Here's another period of oscillation. We can also calculate the point in between. And essentially, once we do that, we can, so we know it's going to go up here. And then we can also calculate C and sketch the process as shown here. So given a transfer function that's second order, we can go through this process and sketch the response. If we have a process response, we can go backwards and calculate the transfer function using the same method, except it's just going to be in reverse. We get the rise time, we calculate the period of oscillation, we determine the overshoot, we determine those necessary parameters, then we calculate these terms, gain, and then we write the transfer function, right? So we can now do that for a first order and a second order process. If we look here, this can go through, this goes through an example. I'll just, instead of me writing it out, I'm just going to say, here's the process that I would go through is I'm first going to get KP based on what's given. I can also, so it's told where it has a 20% overshoot. So if it overshoots by 20%, that means I can now get zeta based on the overshoot. I can, let's see, so based on, and next I'm going to need tau. So I can get tau using the period of oscillation. Because then I need to know tau. Once I have tau, I can calculate the T rise. If the process has a dead time, which we haven't talked about yet, we can go ahead and get that. But now we can, based on this right here, actually, I should say that we don't really need to do this part right here, but I'm just going to put it on here because it's general. So this is going to be our term for the dead time. If this is appropriate, if we calculate t rise and it doesn't match the actual time that it takes, then we can know the process might have dead time. We'll see what that means a little bit more next time. Once we have these terms and we know it's an ideal second order process, obviously we can write the transfer function. I wrote this right here as tau n, but we were calling this tau p, so I'm just going to call this tau p. Okay, so second order process, we can go both ways. First order process, and we can go from the response to the transfer function. Now so those are the primary two types of processes that we can look at. Before I go to higher order processes, I also want to mention we can have processes that are integrating processes. An integrating process is a process that doesn't reach a new steady state. So essentially what happens for an integrating process is you make a change and the process just changes. I don't have a slide on this, but I'll just kind of point out, you can think about integrating processes intuitively. So for example, a level in the tank. If you apply a step change to the output of a level in the tank, you know that the level in the tank is going to linearly decrease. Okay, so integrating processes, you can sketch their dynamic response from the transfer function intuitively. You just have to recognize that the transfer function is an integrating process. And a transfer function that's an integrating process is just like a 1 over s type process, which is a linear process change. Okay, that said, I wanted to mention that before getting too far. So we can look at higher order processes. So anything higher than a second order process, we're going to treat a certain way. And we're going to treat these as what's called first order plus dead time models. If we look at, again, and these would be overdamped higher order processes. So for example, if n equals 3, the process is going to look like this. If n equals 5, there's going to be a lag, and there's going to be a little bit of delay. For a 15 type process, there's going to be a long lag. We are going to treat these as what's called first order plus dead time models. And what that means is that essentially we're going to say that the process has a lag for a certain amount of time, and then it's going to respond as first order. Okay, and so this will be our way of representing the process, which isn't perfect, but it gives us a pretty good representation of what it is. So like you can see here is the longer, the higher the order of the process, the more lag or delay that it has, which is why we can essentially treat these as some sort of dead time type models. Example of this could be like a distillation column. So in a distillation column, you might have many stages in this process. If each stage has a representation between the input and output concentrations as first order, you would expect the way the composition changes from the bottom to the top to go through all of these different processes, which would give rise to some sort of 15 plus order process for how the concentration changes with respect to an input. This slide right here just essentially sort of tries to describe what dead time means. So if we have something where we treat the process as like a reactor, and we know that at some point in the system is well mixed, so the concentration in here is Ca. If there is a length of pipe, so let's just say we don't have a composition on the tank, but we have a composition analyzer some time period down over here, we will know the composition once it travels from the exit of the tank to the analyzer. And the time that it takes to travel here depends on what the velocity of the fluid is. It depends on the flow rate. It also depends on the length of pipe. It also depends on the cross-sectional area of the pipe. So there's going to be a time lag, and this is essentially like a dead time. So what this says is that the composition of the sensor at this current time equals the composition over here some time period ago. Okay, so that's essentially what dead times mean. It's just sort of a delay in the response. So we're going to use that. So remember that a dead time, so transfer function for first order plus dead time, so first order plus dead time. Remember, we have our input, And again, if our input is, let's just call this F. So if F is our input, this is going to go through, and we can write it any type of way. It goes through a dead time. So it would go through a dead time process, and then it would go through a first order process, and whatever our output would be coming out. So maybe temperature. So this could be the temperature, and you can switch these around. It doesn't really matter, but we know that if the input to a, so if we know the output to this process is the input to this process, we can just multiply these two things together to have a first order plus dead time model. And so essentially that's what we're doing here. So we're saying that a first order plus dead time model is going to have, right, so we apply a change at this right here is t equals 0. So at t equals 0, there was a change in the input to the process. You know, so the dead time means is that, okay, we're going to assume that there was no change made for some sort of lag period of time. And then after that, we're gonna say the process responds that looks like this. Now, what you can see is that we actually compare this model to an actual fifth order process. There is some deviations from the model initially above the process, and maybe there's some deviations over here as well. But on average, or as a whole, this fairly accurately represents this overall process, minus some variations as we showed there. Okay, so the transfer function for a first order plus dead time model is, again, we know the transfer function for a first order model is Kp over tau ps plus 1. So G FO P dt equals this times dead time. So the Laplace domain model for a dead time is going to be exponential of the, I think it's exponential of negative theta times s. And I didn't give myself enough space to write here, so let me just write this clearly so that it's, so Kp times exp negative theta times s. Okay, so this is the first order plus dead time. So this right here is dead time. The first part of it, including the denominator, is the first order. Okay, so this would be the model. So again, now how we calculate this, again, this is going to be specific for a first order plus dead time model. If we are given, I'll just say, like, given a first order plus dead time model, we can sketch the model response essentially as shown here, because we know based on the value given here in the exponential, we can get the dead time. We have the gain. And so essentially what we're going to do is we're going to treat the first order process as it starts after the dead time. Right, so again, we still have this same thing. So this is going to be our step change A times the gain, or we can say delta U times the gain. And then over here, again, we can look at 95% and we can look at 63%. And this right here is going to be tau P. And then this right here is going to be 3 tau P to get to the 95% mark. And at some point, it's at the new steady state. Now, if we're actually given process data that looks like this, so given this is the data that we have, now we have to actually use a slightly different method in order to determine what the values are for, again, tau P, theta P, and Kp. And this is all based on fitting for what a general model would look like. Same thing, we can get Kp is just delta Y over delta S. We don't have to worry about that. But then what we can do is we can calculate 1/3 of delta Y. So this right here is, we have 1/3 of delta Y. I'm just going to do an X. So this right here represents 1/3 of the total change, or 2/3 of the total change and 1/3 of the total change. And then we can go read down to the time axis and calculate what is the time to get to 1/3 and 2/3 of the change. And now based on these time values, we can determine tau and theta P. So the tau P of the process is this difference divided by 0.7. Then again, theta, so the dead time would be shown here. Okay, and so then the model for this response right here would be G of S equals, well, it would just be, yeah, the same thing that I wrote on the previous slide. Oh, here's the integrating process that I briefly mentioned before. So again, like I said, if we have an integrating process with a transfer function that looks like this, we can just sketch the dynamic response for the process. It's going to look like this. There could be a dead time, right? So this one right here, the level starts decreasing right away. If our integrating process has a dead time, you know, we would just kind of extend this out to the dead time and then have the decrease in the process. I'm going to skip this one for now, right now. So this is integrating process, and I think I'm about to the point where I want to wrap this up for today. I'll mention, I'm going to back up a couple slides, and I want to mention something for you. We talked about a first order process, and we talked about first order process, second order process, first order plus dead time, integrating. The last process would be a second order plus a dead time process, second order plus dead time. There's a homework question on this that is extremely important to do. I want to point out that there's only one subtle difference between a second order process and a second order plus dead time process. If you're given the transfer function, you know there's a dead time, so you treat it the same way as a first order. You kind of have your dead time, and then you apply all the characteristics of the second order after the dead time. If you're given process data that might look like this, you don't necessarily know what it is going into it. So what you have to do is assume that it has a dead time. Okay, given process data, you have to assume that it has dead time. So assume there is a dead time. Okay, the second thing is look at dynamics. So look at the dynamics, the value of R. And what I said right here is this right here is the value of R. The time that it takes to cross a steady state. Now, if this is an ideal second order process, if there's no dead time, when we calculate T rise, it'll be equal to R. But we can't calculate T rise until we first know, so we have to first get theta and tau, or we have to get zeta and tau. Once we get zeta and tau based on the period of oscillation in the overshoot, we can use that to calculate T rise based on the equation that I gave you, and we can compare T rise to R. R should be at least bigger than T rise. So if R equals 10 and T rise equals 5, then we know that theta equals 5, right? So that's how we would determine whether a second order process has dead time or not, right? So that gives us, that kind of completes the number of models that we can look at. This isn't what we're going to talk about here. This isn't an actual model, but this is just, you know, maybe a discussion of sometimes we might have an inverse acting process that we have to model. So if we have a process that's inverse acting, it's going to show up looking something like this. So at time equals 0, the process initially responds negatively and then it responds positively. We would essentially have to fit this using two first order processes. So if you can imagine a process, so one process, for example, might look like this process right here. If we assume that we have one of our processes is going to look like this. It's going to respond very fast, and it's going to respond like this. Our second model process is going to again, once the time period has changed, it's going to have a slower response, but it's going to go a little bit higher. If we add these two things together, we essentially have, well, so this first one, let me redraw it. This one would have to be a little bit faster than this process respond. I mean, this looks like it's responding in negative time, but don't worry about that. We add these two things together, we would get this process that looks something like this. Okay, and then we can essentially take the characteristics of these two, and again, we would essentially add those together. This, I would write this as plus, and I would write this as minus, because this process has a negative gain, this process has a positive gain. We just add those two things together, and we can represent this process. You can also have recycle processes. I mean, these are things that we can just derive. What this leads to is longer, larger time constants, changes the game. But essentially, for a recycle process, we don't necessarily have to treat that any different. It would just be affected by the model to the process. Just to wrap this up, this is a review of common transfer functions. Common transfer functions that we've looked at here that include the dead time model. And the last thing that I'll note that, and then we'll stop, is that if we have a second order plus dead time, we would just take this second order process shown right here and multiply it by this dead time model. So that's the only model that's not shown on here for this process. So this slide right here, and again, you can pause and read it. This just summarizes the thing that I said you should be able to do. The only thing that I think may not be mentioned on here is an integrating process, but you can sort of rationalize through that. But in any case, I'm going to stop there for today.